Okay, cool. So thank you everybody for your patience while we work through the technical issues. Welcome to the CSU Lunabotics design review, critical design review. My name is Kevin. I am the licensed sub-team lead, and
my name is Adam. I am the PLE and the software / electrical code.
all right. Next slide. Here is our.
There.
All right. Okay. This slide is just our declaration of a design freeze. As of today, February 18, 2026, CSU Lunabotics 2526 design is frozen pending only CDR reviewer directed changes. The exception approval by PLE and systems engineer. This is basically just saying that, hey, we're not going to go forward until we sit there and consider the feedback that we've gotten from this design review to go forward. So, officers and attendees. Adam, I think you hit my computer too. PLE, Adam, our project manager is sitting up front here. Her name is Hannah. System engineer, stands for Nguyen Min Ho and Andy because he goes by two names. Our mechanical lead is Jared, and his co-lead is Carter. For those of you who haven't heard, they are stranded on the side of the road and are not likely to make it today. Again, electrical lead, myself with Adam as the co-lead. Software lead is David Skosic. He is in a class that he unfortunately couldn't miss, so he'll be here by the time the slides come up, hopefully. Yeah. And Adam is also co-leading the software sub-team. All right, so the agenda for today, let me just turn this off. We're going to go over the mission, specifically the arena layout. We're going to go over all of the, like an overarching view of the systems. We're going to do a sub-team specific design portion. We're going to start with electrical and software and then mechanical at the end. Again, just trying to hopefully give them some time to get here. We're going to go over our testing plans as well as the team and travel logistics to include a total budget breakdown and a Gantt chart. All right, so Adam, you want to go over this one?
Sure. So again, for those of you who are not familiar with NASA Lunabotics, this is a university design competition hosted by NASA and hosted by University of Central Florida, sponsored by NASA. And it's a competition to create an autonomous robot that can navigate a lunar environment, dig lunar simulant soil, and move it to an area where it can be deposited and build berms, which serve as blast protection and shelter for structures on extraterrestrial surfaces like the Moon. So, yeah. This is the 2026 NASA Lunabotics arena layout. So there's a 2-meter starting zone, 2.5 meter excavation zone, 4.38 meter obstacle zone, and then there's a construction zone. So you have to navigate around obstacles in all these areas and deposit soil here and dig in this area. So these are open tasks currently for the team. So these are things that more higher level objectives that we have to reach. Some of them will be met by the end of the CDR. So we have systems engineering paper that was already delivered prior to this a few months back. Finalized components list, each sub-team has a BOM, so that will be gone over. Purchasing components, that will be done after the CDR is complete. And then we have full system architecture finalized, which you will also see each sub-team's individual architecture during this presentation. Design freeze declared, we just did that. safety hardware procedures defined. You will also see our safety standard for software and electrical. And then assembly beginning will happen, of course, after we have parts ordered and delivered. Securing accommodations, that's finances, which we're currently in the process of, it is pending. And then proof of life will happen post all of that. So these are just the general requirements across all sub-teams for the entire competition. So we have to say under 80 kilograms for our robot weight. The power for our the power for our robot is a 25.6 8S lithium iron phosphate battery. Maximum bandwidth for our robot is 4 megabytes per second. We're aiming to stay under that for point deduction purposes. Reliability, mission critical systems need fault tolerance. Obviously, we're doing 10-minute runs, so we have to make sure that we have some safety standards when we're running autonomously. Maintainability, we have a lot more modularity than we did in previous years, which you'll see when we go over the mechanical subsystem. Telemetry, again, low latency, low data transmission, so that we don't get points deducted for extra bandwidth that we don't need to actually use. And then autonomy and navigating around with hands off gets us more points in the competition, especially if it results in burn depositing. And then we have a TPM table here. This is more just a standardized table to go over different, again, more specific competition requirements, at least that we set for our own team. So we have various requirements. You can read through them. These are things that we want to meet by the time we get to, I guess, full production assembly. So we want all these to be green. And yeah, so there's some things we have verified, of course, like there's things like packet loss, the total system mass, things that we can verify through our CAD and our software that we know are good to go. And yeah, that's it. And then going on to this verification matrix. So these are sort of declarations, again, of things that will be done by the time the robot is fully working. So they're things that have to be done before we can assert that we're ready to compete. So again, you can read through that. It goes through all of the data for software team, the size for the mechanical team. There's some electrical requirements for safety, and yeah, there's different they're for different categories, of course, but that's pretty much that. So now we're going to get into the sub-team specific design. So we're going to go through each sub-team, and you guys are going to see what each sub-team has designed, and then you'll see a little bit of sort of an integration plan as each team describes how they're going to put their individual subsystem together. So first we have the electrical sub-team. Again, I am the co-lead, and Kevin Baldoza is the lead. So we're just going to go over this. So again, this is much like the TPM table in a way. We have requirements for the electrical system to say that we're good to go, we're ready to compete, the robot is operating in safe conditions. And then right here, this is just a generalized list of open tasks on the left. So it's just saying, okay, we have total requirements under this category, this category, this category, and then over here it's laid out what those specific requirements are. And you can read through those if you'd like, but those are just goals that we have to meet come time competition.
Yeah, so on that note, if there's anything here that you see that you would like either a better look at or a longer look at, again, feel free to reach out. We can get you copies of that, something that's a bit more legible than maybe what you can see on the screen, something a bit more complete and in-depth. And given the amount of people that we've got today, I think we're good to have questions open throughout the presentation. No need to wait till the end because we do have a fair bit of slides. I don't want to have to keep backtracking all the way up and down. So I don't think we have too many people where we need to save questions till the end. I'm going to leave it open. So feel free to raise your hand or interrupt or whatever. So. All right, let me do this one.
Sure.
All right, so here we've got our system fault table. We've got three main components that we're looking at least on the electrical side, where we are anticipating, I guess, are likely to fail, not likely, but are most likely to fail. So starting off with battery, we've got battery under voltage and over current. And let me rephrase this. So with this table, we've got it divided up by component, fault, subsystem, severity, troubleshooting, and resolution. And the goal of this table is basically just to say if something fails, we have a plan of action in place to be able to address it, right? I don't really want to go into all of them because that would take forever. Feel free to read through it and let me know if you have any questions. But the main goal with one of these is to be able to have it with you, be able to go over it before the competition and during the competition so that if something fails, you're not just sitting there trying to think of something off the top of your head. You have a predefined method of troubleshooting and hopefully resolving that issue. All right, so here's our subsystem diagram. To kind of give an overarching view of what we're looking at on the electrical subteam, we've got mostly focused on the 24-volt system here. We have a 24-volt, like Adam said, lithium iron phosphate battery that supplies power to the power distribution board, which then transmits that power to all of the individual 24-volt components on the robot. What we have shown, at least here, kind of on the left side, is the 6 drive motors and their drivers, and then the 3 actuators we're going to use to actuate the bucket, be able to actually excavate dirt. So something else shown on here is the CAN bus. We're going to go over that a little bit more later, but you can kind of see a visual here. We're going for a hybrid ring star topology. Again, we'll go a bit more in depth into that later. And then you can also see some of the signals, some of the other miscellaneous signals going on, like the encoder signals from the actuators themselves and the RGB cameras and depth camera, as well as the IME. So, all right, speaking of topologies, we have our, like I just mentioned, the ring star hybrid topology. This kind of goes over a little bit about why we chose this. Each of them has their own different, I guess, benefits and drawbacks. The ring topology, you can see it over here. What's a little unique about the ring topology, as opposed to maybe the bus topology, is that if you have a break anywhere in your line, I guess your communication line, signals can still travel around the other way. You know, you're not, like, it adds a layer of redundancy to the CAN system itself. And that's going to be used to support the drive motors. The drive motors, can you go back one slide? You kind of see the drive motors here. They are in a configuration that makes it a little more ideal to use the ring topology, because you can just kind of do a little circle. This is kind of laid out how the robot's going to look. We skipped the mechanical slides. That kind of messes with what I had going on here, but basically all the motors, would be like the left side and the right side, and we'll just run the CAN twisted pair all the way around the bottom, kind of inside the chassis there. So it has lower material cost than a star topology because you are still using one singular bus, just connected at the ends. But we are also using a star topology specifically for the actuators. The actuators are going to be on the end of the bucket. Again, it's kind of, do we have something real quick we can pull up of the, go to the enclosure slide. Again, I apologize, it's just that we skipped the mechanical slides. So you can kind of see it here. These would be your drive motors, ring topology, kind of run along the inside here. Our main node, if you want to call it that, is going to be inside the electrical enclosure here. We'll go into that more later. But the star topology kind of comes into play for the actuators here. So we've got these two shoulder actuators mounted to the bottom of the chassis, which kind of raises the whole beam up and down. And then that would, ideally, each of those would be on their own star node. And then we would have one more star node running up the arm here to actuate the bucket linear actuator. So the star topology, again, a bit more reliable than the bus topology in that if one of the lines has a disconnect or a break in it, then you're not, you don't lose connection to every device after that on the bus. So it makes it easier to add and remove components and has a bit better properties in terms of like actual communication on a very cluttered high-speed bus. So, all right, I'm gonna let Adam go over the BLDC motor controller.
Okay, so this year we're developing custom BLDC motor drivers. They're 3-phase DC motors. So this is just a general component layout. It's for anyone technical. So there's a buck regulator on the board itself that does the 24 volt down to 5 volt, and that's just for all of our auxiliary devices on board. There's another linear regulator on board that also steps down the 5 volts from that to 3.3 volts for things like our primary microcontroller. The next thing is the LTC 4359 ideal diode. That's I have everything color coded so you can see, but that is basically where the power input comes through, and it allows no reverse current. I mean, there is reverse current, but it has like I think it's a 300 nanosecond dead stop, so there's basically no reverse current that's going to get through that. And then we have TVS diodes on that as well. And then there's DC link capacitors that go directly to the power for each phase, which are the big bulk electrolytic capacitors you can see there. So that provides power to each phase so that we're not like browning out as we try to pulse each phase. And then the red is the gate driver, so that's triggering all of the FETs that you can see, which in the green. And then PWM control is coming from our STM microcontroller, and again, it's communicating with that gate driver. It's a smart gate driver by Texas Instruments, and with that we have sort of a smart BLDC custom driver. So then there's a few other parts. Like I said, there's an STM on board. The STM does support CAN natively, so we're going to try to utilize that for these boards. And then there's a ADC on board, which is basically just taking voltages from that driver chip, and it's giving us current readings from each phase. So each of the 6 motors will have 3 current readings, 1 for each phase. So we'll have a pretty accurate idea of how much power the motors are pulling, and also we can log that and keep track of our power usage and compare it with the meter on board for telemetry purposes. And then this is just a schematic for that board design that you saw, Altium Designer.
All right, so I'm going to go over a little bit of the linear actuator controller design. I'm not going to get too much into the STM32 and some of the power regulation because a lot of that is just borrowed from the BLDC driver, which we already went over. So, but okay, yeah. The voltage regulation is borrowed from Adam's BLDC driver. However, we will need to add an additional 12 volt step down converter because of the fact that the actuators run on 12 volts and everything else runs on 24. So the H bridge, there's not really too much to talk about with the H bridge. It's an H bridge. It's got reverse polarity protection diodes. But as far as sensing goes, that's kind of that IC up in the top there. That's what we're going to use to sense the power draw from the actuator itself. It's an op amp that's like kind of optimized for current sensing, high side current sensing specifically. Comes in predefined gains of 20, 50, and 100 volts per volt. I think up there we've got 20, but since then we've switched to 50, just kind of use a little bit more of our range of the ADC in the STM32. So, and then as far as sensing position / extension, the actuator has a built-in Hall effect encoder with a pulse rate of 17.4 pulses per millimeter of travel. So relatively high resolution, not super great, not terrible, but enough to where I think we're going to be well within like any tolerances we would need to meet in terms of the 2 shoulder actuators moving one maybe a little further ahead of the other. So that's all going to be handled by the STM32. But all right, next slide. All right, and then control, again, the STM32 will receive position commands through the CAN bus, and it would also send periodic power consumption data and fault messages over the CAN bus as required. So up there, you can kind of see we have a digital SPDT switch. So the purpose of that is instead of having 2 different PWM signals on 2 different pins that the STM32 could generate, this basically allows us to use 1 PWM signal and a different pin to select to which FETs that signal goes to. And part of the reason for that is that it mitigates the risk of a shoot-through fault. So you have like a hardware, you have a hardware what's the word I'm thinking of, like safety, so that you don't turn on two MOSFETs that shouldn't be turned on at the same time. And then the half bridge drivers, we have two half bridge drivers. They're kind of set up in a funky way, so I'm not going to go too much into it, but basically, you know, they drive, two of them make the full H bridge. They do have built-in shoot-through protection though, so that's another thing, another little layer of safety. So, next slide. All right, then the housing and the enclosure. We discussed making an in-house enclosure. We opted not to do that. We found this one, which we believe will suit our needs just fine. It's a roughly, what, 14 by 10 by 6, what is it, ABS enclosure?
It's a ABS PC like combination, so it's like a custom plastic alloy that this company makes for outdoor.
Okay, it's got some fancy plastic that is a little more impact resistant. It's got better UV weather durability. It is IP66 rated, which is really the key thing we were looking for. Anything IP6, whatever rated, basically just completely resistant to dust ingress. It's UL94 V0 rated too, so if something does, you know, cause it to catch on fire, it doesn't pose a huge safety risk. And it's got a latched hinged door, so we're not undoing screws or anything to get into it. If we need to change something, fix something, whatever, it's pretty easily accessible. You can kind of see where it's going to be mounted here on the back of the robot. You can't get a great idea. It is a little dark with these lights, but you know, easily accessible, out of the way, all things like that. You want to go with power budget?
So this is a rough power budget of all the high power electronics in the robot. As you can see, we just have like sort of like quantities for each one. So obviously there's 6 motors, 3 linear actuators. These are estimates based off the max power of each device, and then we have a duty cycle, which is sort of the estimated amount of time that we think the device would be used in a single cycle. And when it comes for the total, we have 409 watts, and with our, I believe it's a 640 watt hour battery, that gives us about 90 minutes of runtime. Now, even if we somehow use double that, saying that, let's say we use the motors at full capacity, at full tilt, we even at half that time, we still have more than enough battery to go through a full cycle. So our battery capacity is definitely large enough to get through 1, if not 2 cycles without charging. So we should be good there.
I can do this one if you want. All right, so here's our safety slide. This basically just outlines the procedure and some of the hardware we're using. We'll get into software safety here in a little bit, but as far as procedures go, PPE, all maintenance, any assembly, anything that needs PPE, we're going to be wearing PPE. But specifically for the assembly, everything's going to be done with energy storage devices disconnected or discharged. Same thing with general maintenance. General maintenance basically is just anything pre-competition maintenance, you know, whether you're testing, something like that, where you're not time crunched. You can pretty easily take apart the robot while not being super stressed out. So again, battery disconnected, passive energy discharged. Now, when we talk about field maintenance, I'm talking specifically about maintenance done at the competition. So, you know, when that happens, you're usually on a time crunch. You're usually like, hey, we have like, you know, 10, 20 minutes, we have to be there, and we need to get all this stuff done. So, a little caveat here, maintenance can be done with the e-stop depressed if and only if there is somebody else who is actively watching or making sure the e-stop button does not come undepressed while you're working on it. Just having 2 sets of eyes on the whole thing, really. And again, make sure all your energy is discharged before you go touching things like capacitors. Safety devices, we have a competition required 40 millimeter diameter red e-stop button that latches. So kind of self-explanatory, cuts power when you hit it, doesn't come undone until you twist it. And then we also have an operation indicator, which we don't have a picture of, unfortunately, but it's just kind of like an industrial tower light, red, green, yellow. And that's mostly for situational awareness during testing and doing things where you're not in the competition, but the robot's still moving. It is a big robot. It is kind of heavy. It does have motors, which are, you know, they're kind of strong. They're not, I don't know if they rip your arm off strong, but they're pretty strong. So having that additional layer of safety, especially if you're gonna have your fingers in there working on stuff, so.
Question about that. Are
Yeah,
you
go ahead.
concerned at all about ESD?
ESD as far as us touching the robot or the robot touching us with ESD?
Either.
Either? Not
No,
particularly. In
touching
terms
the
of
robot.
ESD for the electronic components, everything should have ESD protection on anything that has pins. So you can connect two connectors together, and if for whatever reason some ESD had built up, it's not going to damage anything inside the robot. I'm really not too worried about ESD on our side. That's maybe you're thinking of the capacitive energy. So like when you have capacitors, big capacitors like the ones on the BLDC drivers, some of those can store a fair bit of energy. And usually when we say discharge capacitive energy, that's basically just putting something conductive that has a layer of insulation between you and the conductor on the pins of the capacitor. So that discharges everything, makes it safer to work with, all that good stuff. Any other questions? Okay, here's a little bit of our monetary budget. Our total components budget is around $2,300. Harnessing is about $220, and the custom motor controllers are about $84, for a grand total of roughly $2,600. So you can see kind of an itemized list of what we've got right now. Does anybody have any questions on that? Yeah.
Your motor controller estimate, is that per or is that for the total number you're making?
I mean, it's broken down. There's a unit cost and a total cost.
Yeah, but I think he's looking at the top one.
Oh, the top.
Yeah, the unit cost, that is, well, that's a great question.
Well, so sorry. We're gonna be ordering one motor controller, like worth of parts for prototyping, and then we're gonna batch order 6 or however many we order for the actual robot. So it will be technically 7. So there's an additional for prototyping. That's what the top shows.
So you're only gonna have your one prototype as a spare?
No, we'll order enough components to build multiple. Like the 6 up there is actually enough. Is the cost to build? I think it's somewhere between 8 and 10 because we have to order in bulk. So the cost that we have, you can't see it here, but there's a spreadsheet where we have a digit key order laid out, and it's enough to build 10.
I think maybe this specific bill of materials may have come from the confusion of, at some point we were told that we needed to put together a budget of roughly $1,000 worth of items that were going to get ordered immediately, only to find out that it was just a random budget of budget of items totaling $1,000. It was confusing. Carter's not here to talk about it, so I'm not going to go too much into it.
But regardless, yeah, there will be the actual order placed for all of our competition drivers, and then we'll initially probably buy a prototype unit.
Does that answer your question?
So risk and mitigation, these were topics that we covered in our PDR originally. So the idea is that we're showing how we mitigated some of the risks that we had with our design decisions. So the current ones that we reduced reduce the risk of are power surges. So like on our various components, like the motor controllers, the actuators, we have like I said, the ideal diode. We have TVS for static and various other things. So there's a wide power range that these devices can take in, so that they can handle these types of things. We have filter capacitors and stuff on the inputs of devices. So there's a lot of filtering and redundancy on those. For battery overdraw, like we said, Kevin will get into it later. We're looking into creating a smart power distribution board, so that should handle anything in that regard. I guess the battery, if it gets too low, obviously we'll have software faults so that we can't run the battery to a dangerous limit, but that's that. We have multiple routes there. Then for motor stall / overcurrent, our motor drivers, the chip that drives the motor has Hall effect sensors and current sensors built in. So we'll have the physical hardware layer of protection, on the motors, and then we'll also have a software protection so we can limit the amount of current that the motors could draw as well. So there's 2 layers there. And then, of course, we have e-stop and power logger failure. So we're going to be recording our power data on the robot as well as externally with a different device. So we have 2 means of recording our power data, and then we also have 2 means of e-stopping, I guess. We have a software e-stop and a physical e-stop, which you'll see during the software slides. It has a specific name.
Yeah. Okay. Well, because Adam brought it up, I'll talk about it. I wasn't going to talk about it, but I'll talk about it. Something that we recently decided that we wanted because it would be good to have is a smart power distribution board. Now, again, this idea wasn't fully fledged enough to be able to put it in the slides, but I can talk about it a little bit as far as our reasons why and the methods we plan on using to implement this. The idea is that you have, instead of having like a traditional power distribution board, which might have fuses and lugs on it to be able to connect to it, in addition to those fuses, you would also have an electronic circuit breaker that would ideally trip before the fuse. So let's say you have maybe like 8 different circuits on one side of the board. Each of them is fused, or not fused, but has the current sensor on the positive end, which would continuously monitor the current using the same op amp we used for the actuator driver boards. So now we would use an ADC to be able, the ADC and the op amp would both feed into a comparator once the op amp output voltage, which is directly related to the current through the circuit, passes a certain threshold, which would be set by the ADC. The comparator, flips, actually also flips a latch, which turns off a MOSFET on the low side. Now I know I'm trying my best to explain it without a picture. Again, I wasn't going to talk about it, but basically what that allows us to do is it allows us to give different components a good hard reset. Basically turn it off, turn it back on again. Let's say we lose communication to one of the drivers. We don't know what's going on. It's not sending any CAN messages or anything. We're not getting any responses from it. We could always just from the power distribution board, turn it off, turn it back on again, and hopefully that would fix the problem. And if it doesn't, then you'd go forward from there. But that's kind of the idea behind it. Again, I wish it was a little more fleshed out before I talked about it, but
I have one more thing to add to that. The main idea with our previous experience is that having a smart power distribution board would allow us to technically have firmware on board that would trip the computer's power if it's not sending signals. So we've had issues in the past where we lose our computer to either to a brownout or it just freezes or something, and we have no way to reset it. So if we have a system where if the computer's frozen or off and it's not sending signal that the power distribution board knows it's not active, it can perform a hard reset with the power and hopefully get us back online. Because if we lose our computer, then we don't have a computer. Yeah.
All right. David?
Okay, so now we're on to software. No. Okay.
All right.
So I am the software co-lead, and we have David here as software lead. So yeah, you got it.
All right, you ready?
Like the electrical team, we have a feature verification overview. So with software, there's different packages that will perform different operations on the robot. And so I have it laid out by package here. And then these are sort of declarative statements that say what each system has to do by the time we get to the competition. And that way we can say that we can safely operate the robot the way we design it to. And yeah. And then this is a summary of that slide, so it's just showing the different tasks per category, and then the ones that are in progress, the ones that are not open yet, tasks that haven't been started yet. So in progress, we have camera software started, localization software started, some hardware interface software, and then integration is always happening when you're building these things, so that's also in progress. So starting with the computational side of the robot, we are using a NVIDIA Jetson Orin AGX provided kindly by Kevin. So I just have some specs here. I know not everyone is going to understand the specs, but this device specifically for AI use has 275 teraflop capability which is like data transfer like within the computer. So you can have very, very high data rate AI models run on this device, and then has 64 gigs of RAM. And then it has onboard GPU with 248 CUDA cores, 64 tensor cores, which is very convenient for AI. And it only draws 15 to 60 watts at max capacity, which is, for a computer this size, is pretty good. And it takes in as many video inputs as we need. There's different types of inputs based off of what kind of like camera you have. So it can take in 2 4K cameras or 4K 30 FPS cameras, et cetera, et cetera. So we're using 1080 cameras, and they're probably going to be lower res than that, and it can already do 8 of those, and we only have 5. So we know that we're good there. But yeah, that's pretty much the computer. Going into the auxiliary devices on the robot. So what we're doing with this robot is we're going to have a depth camera on the front here, and then we're going to have so depth camera, if you don't know, these are RGBD cameras. So what it means is you get RGB video, which is like it's the same kind of video you take on your phone. But you also get a depth layer, which is sort of like a map that tells you how far away things are from you. So the front camera will be an actual depth camera, which is that larger camera on the right. And then the other 4 cameras are going to be regular webcam RGB UVC cameras, which just means that they don't require drivers. You just plug them in and they work. But the problem is we need depth all around the robot. Like, we want the actual depth camera to be in the front for accuracy, but we need these to give us depth data. The problem is we don't have the budget to buy 4 more depth cameras. So what we're doing is we have the 4 cheaper cameras. We're gonna actually run the RGB standard camera footage through an AI model called Depth Anything, and it turns regular camera footage into depth data. So we actually will have 1 real depth camera and 4 synthetic depth views. And then I'll get into the hardware architecture later, but that's how our sort of peripherals are gonna work. And then the robot will also have an IMU, which will be purely for acceleration and velocity. We're just gonna feed the AI model its current velocity and current speed and current acceleration, and we'll train it on parameters that we want. Like, we might not want it to accelerate super fast, so we'll positively and negatively reinforce it based off of how we want it to perform. So going into like the software side of the I guess the visualization, we're using RViz. So let me start with this. We're using ROS. If you don't know what that is, it's Robot Operating System. So we're using ROS 2. It's a framework for robotics that's used in industry very commonly. If you've seen like robot dogs or like Boston Dynamics, it's all NVIDIA powered. So we have RViz, which is like it's a visualization library inside of ROS. It allows us to view our cameras while we're debugging and developing. And then that depth camera we use is made by a company called Orbec. So we have to use their SDK, it's their special software package to actually operate the camera. And then, like I said, we're using a library called Depth Anything. This one says V2. I actually found out there's a new library, V3, but it only runs on NVIDIA specific hardware. So we'll be running the latest version of this AI library to convert our RGB image to depth data. And then, like I said, on the other side, this is an NVIDIA computer, so we have CUDA cores, which means we can do some very quick, very insane graphics processing. And then, as far as like the development side goes, software side, we're using Docker containers to pretty much make it so that we can have like a virtualized environment on our laptops as we develop, and it's easy to transfer code between computers and upload it to repositories and such. And then we can just take the container, package it, and move it onto the robot so that we're not dealing with like file path issues and like installing dependencies. So it's all just like plug and play. This is NVIDIA. No, I'm sorry. So then, like I said, we're using NVIDIA's computer, the Jetson Orin. So they also have a software suite. They have the Isaac Sim and Isaac Lab, and pretty much this is a platform where you actually build your environment in a simulation. So you will build the arena that we'd actually compete in a simulation. We rig the robot in simulation, and not only is it just the physical elements of it, but we actually rig the cameras that would really be on the robot in simulation, and we fake all of the data, the video data coming from the cameras virtually. So we can actually train the AI, instead of training in the real world with real cameras, we can train it completely in simulation with the actual software that would run on the robot in the real world. So yeah, and like I said, Tensor RT Tensor is just like a type of it's a type of core on like graphics processors, and it's really good for running AI models. I'll get into it later, but there's all sorts of quantization you can do with the data that goes into AI and optimizing it for speed, but that's what that does. So I'm not going to go through this completely in depth. This is more for documentation purposes, but this is much like all the subsystems, the packages you saw for software. This is sort of how they route together. It's kind of hard to see. I'll just go through what this says. So everything starts with the perception module. The perception is where all the cameras come in. It routes to localization, which is where we basically we figure out where we are in our free space. We also will have April tags, which are just like little QR codes that will tell us where we are in space. So from our own map and then also the April tag, we should be able to figure out like our general position. And then there's mapping, so that's going to be taking the raw camera data and turning it into actual 3D depth, like a 3D map of everything that's around the robot. So instead of just camera data, it's an actual point cloud of like the area around us. That all gets fed into navigation. So navigation will actually just be our AI layer. So the AI will teach it how to drive around and will reward it for operating in the conditions that we want it to. And then we have hardware interfaces at different nodes. So that's taking in devices that aren't the cameras. So that would be like our gyro, some sensor data for like the current sensors, anything else we add to the robot. There's a data layer, so it takes all that data and it basically publishes it so that we can use the data. So if we're collecting data on power or collecting data on current or anything, we can find it there. There's a fault node. So basically the fault node will just trigger certain things with the hardware based off of what the fault is. So like if the motor causes an overcurrent, then the fault node will send a message to the hardware interface to tell it to stop the motor. Then there's a Wi-Fi node. It'll take data from the data node, and it will transmit it to a telemetry node. And then we have control state. Of course, this robot is going to be autonomous, but we also have to be able to drive it manually. So we have to be able to switch that state in case something goes wrong. And then we have manual control. So I'm not going to go through all this. For every single thing I just described is called a package. So each package, go to the next one. So this is the package we're working on right now. So inside each one of those is the actual structure for how the software is laid out. So each package has nodes, and the nodes are what actually perform the different things. So I'll go through this one because this is the one we have built right now. But pretty much we have USB cameras coming in at the top here. They all go into nodes, which basically publishes the camera data. It transmits it across the computer. And then what happens is this, they all feed into that depth node I was talking about. So they all go into the AI layer that turns the regular cameras into depth data. That all gets fed into, that's the output for this one. So all of this data gets output. And then over here we have the actual depth camera, and that just goes through the SDK that runs the camera, and then it gets transmitted out. So the output of this entire package is takes in the cameras, and then it outputs all the depth data for all the cameras. So like that's how we sort of wrap the software. You have like a goal for the input and a goal for the output, and then all the processes that happen on the inside. So I'm not going to go over all of it, but if you want to scroll through it, we have one for localization. You can keep going.
Okay.
Yeah, there's one for mapping the navigation. It's all the same stuff you saw in the higher level diagram. So yeah, I'll go over this one. So this one takes in commands from the AI. So it's taking in the velocity, for example, from the AI. It's running it through a motor controller node that processes those commands, and then it sends them to the motors. And then there's also more data coming in, going to a sensor reading node, and then publishing that data as well. And then, of course, the motors are going to be sending CAN data back. So the data from the motors has to come back here, go to a node that takes that in, and then publishes it to a telemetry node. And then, of course, we have our output. So we have our motor position, speed, current, battery voltage, IMU data, and then the wheel position. So again, it looks complicated. It's more like a way for us to keep track of the software we're building so that we don't get confused on the processes that are happening. So yeah, there's data, go ahead. And then there's the fault package, the Wi-Fi telemetry package, control state package, manual control package. And then this is a layout of all of those, but just purely in text. So like I said, there's inputs, outputs, so you can actually see the tags in the software where that data goes. And if you were on the computer, you could reference those tags and find the data you're looking for. But that's sort of the layout. So like I said, we're using NVIDIA's Isaac Sim software. So I have a little demo here. So you actually rig the robot in 3D, and then that's in Isaac Sim. And then you go to Isaac Lab, and you actually implement policies to train the robot. So each one of these is a different instance of the same robot that's doing something slightly different. And based off of your reward structure, you reward it or you punish it for performing certain actions. And eventually, after enough training, you get an accurate model that does what you want it to. So if you look closely, each one of those is doing something slightly different. And one of them is hopefully the outcome of whatever that person was designing it to do. So we sort of implemented our own like AI, tests. I showed this in the PDR, but we created a 2D version of what the robot will actually be doing. So we had this little rover that drove around, and it could only see what was in this frustum zone, which is like sort of the camera area. So there's like rocks and craters, and then there's these orbs are just representative of like simulant soil. So if you go to the next slide, this is just a little video of it completing a task. So it picked up the orb and it deposited it. And of course, this is like a very small AI model, so it's kind of dumb, but like it gets the point across. Our actual 3D model will be much more sophisticated. So like I said, the robot is going to take in various parameters. So the robot will take in the 3D, I'm calling it a grid, the 3D grid of like the data from the camera. So it's sort of a mesh of like what the robot sees around it. It'll be taking in its pose, so its XY coordinates as well as its rotation. And then it will know what zone it's in. There's 4 zones. There's the mining zone, construction zone, obstacle zone, and starting zone. So it'll know where it is. And then it'll output the velocity, the speed it wants to travel, and then its position. And then, let's see. From that, we can implement all of that into the Isaac Sim software and train it virtually as if we were running it in the real world. So much like software, or much like electrical, we have a fault table as well. So these are things that could potentially go wrong that we want to have a methodology for resolving. So again, I'm not going to go through all of it, but you can see we have procedures for if certain things go wrong. I'm not going to go through this either, but you can read through it if you'd like. It's a state diagram, so it's basically just going through the processes that the robot goes through. So if we go from startup to manual control to autonomy, and then hopefully with autonomy that gets us to the very end. There's other routes I can take. If there's a fault, then we can trigger a stop, which is we're calling it the e-suggestion in software, because the e-stop. There's a slide for it, So yeah, there's various routes it could take. Like if the autonomy fails, it might route back to the fault state. So it sort of goes through all the possible scenarios. You could map through different scenarios, and it should always land in a safe spot or into a fault state where nothing bad can happen. And then this is a bandwidth budget. So in this competition, you're only allowed to transmit 4 megabytes per second, and you actually get deducted 0.3 times the amount of megabytes per second you send, and they only give us 120 points towards our data. So if we ran at full tilt at 4 megabytes per second with our 120 point budget, we would only be able to run for 2 minutes. Now, like, you're allowed to eat into your other points, but ideally we don't want to use that much more of our points than what they provide us for our bandwidth budget. So I calculated that at full tilt, like as in we're transmitting data back to like our computer to see what the robot is seeing, it would only use 3.7 megabytes because we're not going to be data, we're just going to be streaming a point cloud and nothing else, which is actually smaller than streaming camera data itself. So it'll be easy for us to visualize what it sees, and it's better than streaming just one camera, which doesn't give us that much perception of the robot. So this is the slide that I was just talking about, the e-suggestion. So this is kind of a little joke in the club, but there's a physical e-stop on the robot for electrical, and we needed to coin a term for an e-stop, but in a software sense. So we had issues in previous years with I guess killing the robot not working. Like we turn off the computer and the motors would keep spinning. So it was more like a suggestion. So we're calling our software e-stop the e-suggestion. But this time it'll actually it won't be a suggestion when we use it, but it's sort of a term that is followed. So it is a safety layer that we can kill the robot operations. It would send commands to all the devices on board, the peripherals, like the motors, to make sure that they all stop moving. And then it would put there would be a software layer that would prevent commands from being published, so that the robot pretty much can't move. Let's see. So yeah, this is our budget. We're kind of feeding into electricals a little bit, obviously, because they have a lot of components that we will use for our cameras and other peripherals. But we do have to, get like a drive, NVMe drive for our computer. There's a buck converter that we might need for it to power it because it only runs in 12 volts, stuff like that. So our budget runs us to about $400 for software. And then risk and mitigation, we actually reduced all of our risks from when we set them up in the PDR, which is kind of cool. So the software integration issues, we have a Git repository for our code, and like I said, we're using Docker containers, so deployment of the software is going to be much more seamless than before. So that completely fixes that issue. Autonomy logic bugs. So of course we had issues where we ran the robot with manual control before, and we'd had issues where the motors would be uncontrollable. It would move without command input. With all of our simulation and testing, we're gonna know if the robot's working before it's even like in the real world. So all of the testing and simulation we do will be a prerequisite to that. Communication latency. So that's not gonna be an issue either, because we're gonna have, because of the fault states that we have on the robot as well as the autonomy, the robot will be running by itself anyway. So if we have to kill it, then it's a single command that is sent, and there's tons of redundancy there, because if the robot's running on its own, there's going to be very little we're going to have to do based off of the training that we do. So like, ideally we're going to train it so that it will never run into a wall. So there's going to be very few scenarios where we have to actually kill the process ourselves for some safety concern. And then processing overload, I think it speaks for itself when I say that we went from Arduinos to Jetson Orin AGX, so we will not have processing issues. And yeah, that's it for software.
Mechanical, do any of you guys want to come up and you?
I mean, I can help.
I don't want to make you read all the slides, but yeah, anybody want to come up from the mechanical sub team and present for?
It'd be really funny if I did it.
Yes, it
Let's
would.
not do that.
I mean, I can talk.
We can do a little. We'll cover it real quick. Obviously, we won't be able to go as in depth as maybe Jared or
I'll try
Carter
to go
might,
in depth.
but we can do our best.
And mechanical, feel free to pop in if you have clarity beyond what we have.
So this is Mechanical's model here. So they are using carbon fiber tubing for most of the frame of the robot. The problem is carbon fiber tubing can be, it can undergo stresses and stuff, but like on the edges, you don't want to use like plastic, like mounting components like to connect them, because those will obviously have a lot more tension on them. So there's a company called Dragonplate that makes these 1-inch blocks that actually join carbon fiber pieces together. So I believe there's something like 28 of those on this robot. They're aluminum CNC'd brackets. So that connects like all the various square tubing that you see on the robot. So that's all carbon fiber. And there's some 1/4 inch aluminum plates which are used to make things like this, these like arms that raise and lower the bucket. And there's a few other places. I'm trying to think of where the plates are. There's a battery mount underneath here. That's probably part of the aluminum plate. And then there's also an electrical, like I guess, component mount that will be under here. So I don't think that'll all be 1/4 of an inch, but there will be various aluminum plates on the robot. Wheels, these are going to be 3D printed. They are 14 inches in diameter with the grousers that you see. So the grousers are like the ribs that you see on the edge. So we're going to 3D print these with some sort of PLA. And then they're actually, it's sort of like a composite build, because there's actually carbon fiber tubes that run in here so that the plastic can flex without fully deforming. So yeah, there's carbon fiber tubes that run through all these, and it screws into the center to lock them in place. Yeah. So like I said, these are those in the picture. You can see those CSU aluminum mounts. Let's see. I don't know much about the epoxy. Oh, epoxy bond. They're gonna epoxy bond the brackets onto the carbon fiber tubes. Yes.
Why is it the always a little edgy?
We were looking into using something like nylon because it's way more.
Yeah.
I personally said nylon, but I can't speak to why I mechanically disagreed with that. Allegedly it's because it's too flexible, and the PLA is going to be more malleable than something like PETG, which would be brittle. But I also feel like at this scale, PLA is going to be just as brittle. So I would opt for something like nylon that can actually take the flex in case we over torque. But I'm not the mechanical lead. So we can answer your question in depth more when he's here. Yes.
However, were they on the budget in terms of what they prefer nylon whatnot? Was that gonna put them over or under?
It's the same cost. So like it's really just a matter of like what material do we want to choose. I mean, nylon's probably a little bit more expensive, but it's nothing that would make or break the bank. It's like a matter of dollars. It's not much.
In terms of mechanical's budget, the vast, like probably 80-90% of their budget is going to be the actual carbon fiber rods themselves. If we don't get those sponsored.
Well, we have most of them, but actually those dragon plate
Yeah.
brackets that hold the carbon fiber tubes together, they're expensive. Like they're little CNC brackets, but I think there's something like $20-something per one.
Like $25 each.
Yeah, and we have like 28 of them. So you can imagine that ramps the cost up.
They are trying to get a sponsor for that. I don't know what the
Yeah.
progress is on that, but
There's an email sent. We don't have a response yet.
okay.
No, so last I heard, which I think was like yesterday, we sent a message to Dragon Plate for the sponsor, and Dragon Plate responded with, "We'll consider it." So
Okay.
And didn't they ask for what we wanted? We'll consider it, but they asked for what we wanted.
I didn't hear anything about
Okay,
that.
yeah, to my knowledge, that Dragon Plate had responded, and they had asked for what we were asking for, basically.
So of course they actually aren't allowing like a bulldozer type robot anymore. So like before last year, I mean we never got it working, but the idea was that we would have a robot that would just push lunar simulant soil into the burn zone. You're not allowed to do that anymore because too many teams did that, I think, and it worked.
Also, I think it goes a little bit against like the I guess I don't know.
The idea is that you're
the
supposed to
ConOps, the mission-
you're supposed to transport soil,
Yeah.
not just like chug along and push it.
Yeah.
So it's not as reliable. So we have a full front loader design here. There's two actuators that actually raise and lower this carriage. So like this entire carriage on the back of the robot raises, like it pitches up and down. And then there's a third actuator up here that pitches the bucket. And it's just a lever system to do that. But it was designed so that it had the most mechanical advantage for its size. So the linkages are like at their pretty much their limits for the size of the bucket. So we'll have a good mechanical advantage there. This is data I think from a spreadsheet that of some calculations based off of the bucket volume. So those are just some numerical specs. Volume rate per hour is 0.23 meters cubed. If we only fill the bucket 50%. So that's decent if we can get a few laps, I guess, in the arena in the 15-minute span. Yeah, there's not much to say about that. Transport, so of course there has to be, I believe it's for every 20 kilograms that the robot weighs, you have to have one person transport the robot. So there are going to be mounting points on the robot, like handle mounting points on the robot to, reliably move it around safely. The robot is a lot more modular than it was last year, so it'll be easy to disassemble, take apart and then package it and travel down to Florida for the competition and then put it back together. Yeah, nothing complicated like last year where we had chains where we had to like use rivets and stuff to get pieces on and off the robot. And then this is mechanical's budget, so it's just shy of $2,000. we had to change a lot of stuff because of funding situation. So there's a lot of Amazon links on here, but that's not a bulk of the budget is the carbon fiber, assuming that we have to purchase it.
Over half, almost half, over half of the budget is those dragon plate connectors. You can see they're $24.50. Have a $24.50 unit cost, and it looks like we're shooting for 40 of them. So that's $1,000 worth of carbon fiber rod connectors. So
Hopefully a sponsorship goes
Yeah.
through.
Or even like a partial sponsorship.
Yeah. Even if they can provide
Like
half of
that.
them or
Yeah.
something, that would help. But yeah, that's the monetary budget for them. And then their risk and mitigation. So this is still the same as the PDR, but looking at a digging system failure, again, because we switched to a front loader design, it's more likely that we'll actually be able to move dirt. So that's sort of a risk reduced. Wheel hub failure. The wheels have 6 mounting points on the hub, so there will be no way for the wheel to slip, and it's easy to take it on and off because you just unscrew the 6 screws and then take it off. Epoxy bond failure. We are again using epoxy to connect to the carbon fiber tubes, but because they have sort of like a ribbed geometry, it's more likely that they'll stay because of the surface area. There's a lot more contact with the epoxy and the carbon fiber, and they're both textured materials. And then 3D print failure. This is something that we're definitely, I would say, is not a risk reduced because we haven't tested the wheels yet. We're gonna have to test an actual wheel under load that's 3D printed. And then carbon fiber failure, again, we're not gonna know until we test, but I'd assume that that's a risk reduced if we have spares to replace the robot. So going back to just the general overview for the competition, for testing, we're going to obviously, because we have the advantage of using NVIDIA hardware, we're going to run this in simulation so we can actually get the robot quote unquote working before we even have the physical model built. And the benefit of this is we can do what's called fault injection, where we can actually implement things into the simulation, like have the robot's wheels slip because it lost traction, and actually train the machine learning policy so that it's ready to handle the real world. And then, of course, after that's working, we'll do real world testing so we can take it to a beach, run it in a lab just in the makerspace or something, and even run it in the grass. The goal is that the environment won't skew the AI's decision. It's just how it interprets the environment that allows it to travel based off of its coordinates and such. Yeah.
Alright guys, for some logistical stuff, as you can see, we have 2 types of estimates up here. We have the actual development estimate, which is coming in about $4,500, and then the travel estimate, which is coming in about $6,000. Total estimate $10,500.
Okay.
Yep. And then transportation logistics. There we go. Last year we did take 2 to 3 cars, or we took 3 cars, but we're also planning this year cars down to Florida to transport both team members and the robot actually down. Not us, but in other teams have actually shipped their robot down. We will not be doing that. They have shipped it down with varying degrees of success. Disassembly will either, after the competition, we'll either leave the robot intact for demo purposes, or we'll scrap it for next year's and cannibalize the other parts.
Demo meaning demonstration, not demolition. Anybody that might be confused.
No, like demoing the robot.
Yeah.
Oh, okay.
Not demolitioning the robot.
Yeah.
Demonstrating the robot.
Sorry. All right, and then yeah, I think that's it for me.
Yeah. So as we started the presentation with our open items, so I'm going to go over the items that were closed during the CDR today. So again, the systems engineering paper was already submitted. That's a closed task item, but it's on there because it's a big item, as are most of the deliverables. And then we have finalized component list. So the software has all their components, mechanical has them all picked out, electrical has everything picked out for the most part. So we're in a stage where we're ready to order things. on that same note, we have our full architecture designed. So I mean, it's subject to changes, but this is pretty much how it'll be finalized as we stated at the beginning of the CDR. Design freeze is declared, and so the major components of the design will not be changing to issues and stuff. But and then safety and hardware procedures, specifically electrical and software. Right now, we have all of our fault tables, we have all of our safety procedures, and we have multiple redundant ways to kill the robot if we need to, for safety reasons, for taking manual control. So those are all items that we through the CDR we've crossed off of our main task list. And that's it. Any questions? About anything? Competition, sub-teams?
Any comments, any concerns? Lucky, you look like you want to say something.
Just wondering what you gotta do to join.
You just show up.
If you want to join, you just gotta show up and be willing to learn or contribute.
Andre, you have any questions? The sir in the back, do you have anything to add?
It's got a lot to say.
Anything about like the software safety systems you'd like to touch on, or?
I think should make them actually. I think the nomenclature probably would have more to do, less to do with them not stopping, like the stopping being a suggestion, and less to do with like just legitimate safety standards regarding what classifies as a stop going through hardware. So
Okay.
It's a stop and a stop button.
Okay.
It gets very expensive to legitimately classify like a system as a safety system, but e-stops when they're software based. So
All right, cool. Any other questions, comments, concerns? All right, on that note, I think we're done. Thank you all for coming, for sure. Lucky, something to say again?
I asked you.
Okay, again, thank you for coming.
Thank you guys.
Good job.
Yes. Thank you.